Welcome back to AP Chemistry and our lesson on intermolecular forces. In the last video, we learned about London dispersion forces and dipole-dipole forces. Today we're going to move on and talk about hydrogen bonding. And so when we look at this particular type of intermolecular force, it might be helpful if we imagine a molecule of water. So water molecules basically look something like this. Now, we know that this sure looks like a dipole-dipole force here, because if we imagine what water is like, we have oxygen, and we have two hydrogens there, and we have two lone pairs, these two unshared pairs that are hanging out on the oxygen there. And so this is a very lopsided molecule. So when we look at water, it's a bent structure, of course, has that 105-degree bond angle. And that's why we draw water like this, where there's kind of a lopsided structure to it. And, as it turns out, oxygen is a highly electronegative atom. And so it's a very polar molecule. So we have our partial negative charge on the oxygen side there, and the hydrogens will be the positive pole of that molecule. And so if we have another neighboring water molecule, well, we hopefully can see that the negative side of this molecule here is going to be attracted to the positive pole of a neighboring molecule. So I'm going to draw a little structure there. And based upon what we learned in our last lecture, in our last lesson, it sure looks like this is what we would call just a simple dipole-dipole force. But actually, there's something else going on. It's not just a plain dipole-dipole force. Even though it is a dipole-dipole, it's kind of a very special type of dipole-dipole force. And that's because hydrogen is a little bit unusual as far as atoms go. It is very, very tiny. When hydrogen has this partial positive charge, hydrogen is almost as tiny as you can get for an atom. And because of that, when you have a neighboring water molecule, so if I can draw one of those, well, that actually allows the oxygen to get really, really close. And so that's going to create a very, very strong intermolecular force there. Now, oxygen is also very electronegative. It's one of the most electronegative atoms that's out there. It's also very, very small as far as atoms go. And so that's also going to allow the neighboring molecule's hydrogen atom to get very close. And as we learned in Coulomb's law, also earlier in AP Chemistry, that's going to allow this structure, or rather this intermolecular force, to be very strong. And this is a special type of dipole-dipole force that we call a hydrogen bond. And it is very strong. It's one of the stronger forces that we have. Now, a hydrogen bond is a very strong type of dipole-dipole force, and you're only going to find it in molecules that have an oxygen hydrogen, a nitrogen hydrogen, or a fluorine hydrogen bond. And so that limits it to, a few or fewer types of compounds. Now, normally, hydrogen bonds are a whole lot stronger than LDFs, London dispersion forces, or just simple dipole-dipole forces. In fact, like I said, it's one of the strongest ones out there. Now, this explains why when you have a polar molecule that has an F, an O, or an N in it, those can normally dissolve in water. And that's because those molecules are actually able to hydrogen bond with water. And so they have that attraction, and they can dissolve in water very easily. So just as an example of that, if we think of the NH3 molecule, which we call ammonia. That's a gas, and so here's its unshared pair of electrons up there, and it's a polar molecule, as we can see. And if we think about a water molecule, and I have a little room up here to draw that. Here's a water molecule, and it's got this lopsided structure here. It's also polar. Well, guess what? This negative side of the ammonia molecule can be attracted to the positive side, the hydrogen of the water molecules, and as a result, the ammonia can dissolve in water. Ammonia can actually hydrogen bond with water. And so it's a very strong intermolecular force. It allows that molecule and molecules like it to be water soluble. So let's take a look at this example here. Which of these molecules exhibits hydrogen bonding? Well, it's not NO2, because NO2 does not have an OH, an NH, or an FH bond. On the other hand, ammonia does, as we can see in the diagram we've just drawn. It has 3 of those nitrogen-hydrogen bonds. Oh, by the way, if you forget which molecules or which compounds can have hydrogen bonding, well, think of your phone. F-O-N. Of course, they have to have hydrogen, but they also have to involve fluorine, oxygen, and or nitrogen, as we see in the examples up here. Now let's talk about another example. Here's something that may occur or may pop up on an exam or on an AP test, some other test. A chemistry student observes that NH3, a gas, readily dissolves in water, while pH3, also a gas, does not. Can you explain this phenomenon in terms of intermolecular forces? Well, when it comes time to talk about when something dissolves in water, it usually has to do with intermolecular forces. And you want your answer to include a discussion of intermolecular forces. You don't want to say like dissolves like. That's a common mnemonic aid, but that doesn't really explain why. You want to say why in an answer like this. And so it's normally going to have to do with hydrogen bonding. Well, NH3 can actually hydrogen bond with water, as we saw earlier. On the other hand, pH3 cannot. That phosphorus, it can't participate in a hydrogen bond with a water molecule, so it's not very soluble. So here's a sample answer that you might want to give for a question like this. NH3, ammonia, can hydrogen bond with water because its central nitrogen atom is both small and very electronegative. pH3 has only weak attractions to water. It cannot hydrogen bond to water because the phosphorus atom is larger and is not nearly as electronegative as nitrogen. And so this is an excellent answer because it talks about the intermolecular forces, and it also shows that the student has not just memorized the answer, but rather actually knows what a hydrogen bond is and why pH3 cannot participate in a hydrogen bond with water. Let's talk about another example here. This is a type of question that pops up a lot. Rank the following compounds in order of increasing boiling point. Well, if we think about these molecules here, we know that NO2 has we found that NO2 has an odd number of electrons, and as we've learned earlier in this course, get my pen back up here, it is going to be a polar molecule. And so since it's polar, it's going to exhibit dipole forces and also LDFs, as it turns out. And that's a fairly strong set of forces, but let's compare it to the others. Now, CO2, carbon dioxide, we might recall looks like this, essentially. and it's a fairly symmetrical molecule. It has no region of unbalanced negative charge, so it's actually nonpolar. And so since it's nonpolar, the only intermolecular force it will have will be LDF, London dispersion force. Now, water, we just have seen the structure for that. In fact, we've seen that many times. Looks like this. It is a polar molecule, but it's not just polar. It has that oxygen-hydrogen bond. So it's polar, but it has that special type of bond. It's that hydrogen bond, in addition to LDF, which everything has. And so if we were going to rank these, we'd say that the nonpolar molecule is the lowest. And so CO2, and then the dipole-dipole would be in the middle. And then the highest of them all would be water. And so if we look at the actual boiling points, we'll see that we're correct. Carbon dioxide is very low. Nitrogen dioxide is moderate. Water has the highest boiling point. So our predictions were correct. Let's take a look at one last type of force here, and these are ionic forces. Now, I know that when we say intermolecular forces, we're normally referring to covalently bonded molecules, but this is an important force as well. Now, ionic forces are what we have in ionic compounds. And so in this molecule, or not molecule, but this chunk of a bunch of magnesium oxide formula units, what's happening here is the chunk is being stuck together because of these ionic or these electrostatic forces. In other words, the very strong negative charge here is sticking to the positive charge. Those electrostatic forces are extremely strong. And as a result, ionic forces are the strongest. In fact, they're generally speaking stronger than hydrogen bonds or LDFs or dipole-dipole forces. And that's why ionic compounds have normally by far the highest boiling points and the highest melting points. So if we were going to review these, we'd say that at the very top of our hierarchy would be ionic forces. Anything that's an ionic compound will have the strongest forces of them all. Now, if they're both ionic, we have to go back to things we've learned earlier in the class, like a charge differential. A +2, -2 is going to be a stronger force than a -1 and a +1 paired together. Now, if there's a tie on that, then we go down to the ionic size. And so if we have a +1, -1 looking like this, that's going to be a stronger force than a +1, -1 that's larger in size. And we've learned about ionic size already in this course. On down the hierarchy would be hydrogen bonds. Those are the second strongest type. Now, don't forget, you have to have a hydrogen fluorine, hydrogen oxygen, or hydrogen nitrogen bond in order to qualify as a hydrogen bond. When you go down the hierarchy, dipole-dipole, those are the second weakest. It's got to be a polar molecule. And then the weakest intermolecular forces of all are the London dispersion forces. And that's pretty much the only type of force you have in nonpolar molecules. Now, if you have two molecules that are both nonpolar and you need to break the tie, well, the one that has more electrons is more polarizable. There's that word again that we like to see written on the exam, that you know what that means, that it's polarizable, has a greater polarizability, and has stronger forces. So let's practice again. For each of these compounds, state which type of intermolecular forces would be present. So we'll start with HNO3. Well, sometimes it's helpful to draw the structure. We might remember that HNO3 essentially has, I'm just going to draw it out here, it has a structure that basically looks like this. And I don't have a whole lot of room here, so I apologize for that. But we do have the HN, the hydrogen-nitrogen bond. So It's got hydrogen bonding. But is there something else it has? Well, I hope you're thinking of London dispersion forces, because everything has those. So those are the forces present there. How about barium sulfate? Well, hopefully you realize that that is an ionic compound. It's got the positive side. It has the positive 2 charge, and the sulfate's a negative 2. So those are ionic forces in addition to LDF. How about CH4, methane? Well, we've drawn that structure many times. We know it looks something like this, and it is a tetrahedral structure. Everything is perfectly balanced out. It has no unbalanced region of negative charge, and so it is nonpolar. And as a result, it only has London dispersion forces. Fourth example, NF3. We've drawn this structure before. Nitrogen trifluoride has a polar structure. Looks essentially like this. And since it has this pyramidal structure, it is a polar molecule. Doesn't have hydrogen bonds, though, because there's no hydrogen here. There's no HO, HN, or HF to speak of there, so it's just a plain old dipole-dipole force. Of course, it has LDF as well. So hopefully you can take almost any molecule that they could throw at you and decide which intermolecular forces are there. Well, now let's take this a step further. We're going to take these same compounds and rank them in order of increasing boiling point. Well, hopefully you realize that the one that's nonpolar and has only LDF will be the lowest. And so CH4 has the lowest boiling point. Then we have the dipole-dipole force here. So that would be NF3. It has dipole-dipole and LDF. So next is nitrogen trifluoride. Then the molecule that exhibits hydrogen bonding is going to have a higher boiling point. So HNO3 is next. And then, of course, the one that has ionic forces, barium sulfate, will be by far the highest of them all. So barium sulfate will go at the top of that hierarchy. So at this point, hopefully you're able to take almost any molecule that can be thrown at you and determine which type of intermolecular forces are there. Of course, it helps if you can draw the Lewis structure on some of these molecules, and also rank them or decide what their boiling points are going to be like based upon those forces. At this point, hopefully, you're also able to explain why certain molecules can dissolve in water because of the fact that they can actually hydrogen bond with water. If you like this video or learn something from it, I hope you give it a thumbs up, subscribe to my channel, and don't forget to ring that bell so that you'll be made aware of future videos in AP Chemistry.